In this video, I would like to introduce three laws that we can use to describe how logarithms combine together, and to show examples of using these laws in simplifying and evaluating logarithmic expressions. The first law involves a product. If we have log b of m times n multiplied inside the logarithm, that is the same as log b of m plus log b of n. The second rule involves a quotient. Log b of m divided by n is the same as log b of m minus log b of n. And the third rule involves a power. Log b of m to the power of n is the same as n times log b of m. All of these laws in some way derive from properties or laws of exponents because logarithms are closely related to exponents. They are the inverse of exponential functions. I'm just going to prove the first rule in this video and assure you that the second and third rules follow similar proofs and similar properties. So let's think about the first rule. And let's say we express log b of m as some output value little m. And we express log b of n as some output value little n. Think about the exponential form of both of these statements. We are saying here that b to the power of little m equals capital M. And we are saying b to the power of little n equals capital N. That is simply the exponential form of the equations we just wrote. So let's consider log b of m times n. I'm going to replace each of these with the exponent b to the little m and b to the little n from our earlier equality. Well, think about how exponents with the same base combine through multiplication. We know that b to the m times b to the n should equal b to the m plus n. And then, using an inverse property of exponents that we saw in an earlier video, this is simply equal to m plus n. Log b of b to the power of something equals that something. Well, what is little m and what is little n? How did we define them in the first place? We define them as log b of m plus log b of n. And if you look at all the equalities we wrote down, we started with the left-hand side of law number 1, and we ended up with the right-hand side of law number 1. So these two things must be equal to each other. The proofs for number 2 and number 3 are also based on laws of exponents. Now, how do we use these laws in some examples? Let's imagine expressing log 2 of 5 minus 2 log 2 of 7 as a single logarithm. So think about applying our laws of logarithms. First, I note this coefficient in front of the log 2 of 7. That can be rewritten as an exponent on the 7, on the input value. So now we have log 2 of 5 minus log 2 of 7 squared. We note from our second law above that this is the same as log 2 of 5 divided by 7 squared. And then, of course, I could evaluate 7 squared, and I could express this as log 2 of 5 over 49. So here's how we can express the above expression just using a single logarithm with base 2. I can also use this to aid evaluating some logarithmic expressions. For example, if I want to evaluate 1/4 log 3 of 81, I could rewrite this using a law of logarithms. This is log 3 of 81 to the 1/4 power. 81 to the 1/4 power is equal to 3. It's the 4th root of 81. So this is equivalent to log 3 of 3. which is equal to 1. Log base b of b is always equal to 1. So that's not the only way to get the output value to evaluate this expression, but using the law of logarithms did help in this case. Let's find 2 log 6 of 3 plus log 6 of 24. As it is, I would have trouble telling you what log 6 of 3 is or what log 6 of 24 is. I can't really evaluate those. Those are not direct powers of 6. But using the laws of logarithms, let's combine these. So let's rewrite our first term as log 6 of 3 squared plus log 6 of 24. That's going to be equal to log 6 of 3 squared, which is 9, times 24. So I could evaluate 9 times 24. That's equal to 216. So I have log 6 of 216. And to evaluate this, I think 6, if this equals some output value, 6 to the power of that output equals 216. The power of 6 that is equal to 216 is 3. 6 to the third is 216.